discussion on enzymes. We've considered what proteins are, we've studied protein structures, the constituents of proteins, that are the amino acids, and their properties. What we're going to start today is our study on enzymes, which will cover about 3 lectures, and we'll be studying the enzyme mechanisms of a few enzymes, which will be basically ribonuclease, lysozyme, and a serine protease. As we go along, you'll see what they mean. Now, you've heard about enzymes. You know that you need them in the body for digestive purposes. You need them actually for any process that goes on in the body. Okay? So, whether it's your respiratory process or your digestive process or whatever other process is going on, all of them are enzymatic processes. Okay, so there are specific enzymes that are involved that bring about specific reactions, and you'll see how specificity is extremely important in the way enzymes act. Okay, so basically all enzymes are protein catalysts. Okay, they're protein catalysts in that they are catalytic in nature, but they are proteins. Okay, and what we have here, you know about catalysts. What do? They alter the rate of a chemical reaction without undergoing a permanent change in structure. So, this is exactly what the protein is going to do also. It is going to change, we will see how it exactly does that. It is going to change the rate of the chemical reaction, but the protein itself is not going to undergo any change, even though it is going to bring about a drastic change in the reaction. Now, this is a typical picture that all of you have seen, a typical diagram that gives you the free energy of A plus B. What are these? These are the reactants, and your P plus Q in this case are the products. So, what do you have? You have a delta G of reaction, which is what? It is the G of P plus the G of Q minus the G of A and the G of B, right? It is G final minus G initial. And what is this? This is your transition state, your activation state that has to be, so this activation barrier has to be overcome to get you from the reactants to the products. Okay? Now, if you look at this, there is a specific nomenclature that we have put here, which sometimes is called the dagger sign. So, we have a delta G dagger that tells us that this is the energy of activation for the reactants to go to this transition state. Now, if we have a catalyst, how does this reaction profile change? It changes in such a manner that for the reaction A plus B going to P plus Q, we have now a catalyzed portion of the reaction, a catalyzed reaction in which our activation energy has decreased. In decreasing, what does it do? The reaction is catalyzed. It means that the rate has been enhanced, okay? But the delta G itself has nothing to do with the rate. The delta G, you have to remember, is a thermodynamic quantity, right? But the activation that we are considering is a kinetic quantity, okay? This distinction is extremely important when we are considering enzyme catalysis. Now, what do we have in an enzyme? It is basically a protein that has a specific structure to it, and what it looks like is, if we look at the specific protein, say we have the protein that is shaped like this. We have a particular cleft in our protein. Now, if this is our enzyme, it is going to react with a particular substrate. Now, what is that substrate going to do? Our substrate, let us do it in a different color, is going to fit into what we call this active site. Now, what do we have in the active site? We have in the active site, which is, say, this region here, that is marked with particular residues, specific residues that are going to act on the substrate to give you the product. But the enzyme will remain as it is, because remember, the enzyme is a catalyst. So, what do we have? We have the active site that is lined with residues, and it sometimes contains a cofactor. We will see what these mean in a moment. the active site residues have several important properties. Now, this is what we have to be particularly careful about. So, the residues that are in the active site of enzymes have specific charges. So, the charges could be partial, you could have dipoles, you could have a helix dipole, because we have to remember that the specificity of an enzyme is the reactant that is coming to act on the enzyme. So, that is going to have specific groups. Okay. The specific groups will interact with whatever residues line the active site. So, we have charge, we have pKa. Now, if you remember when we studied amino acid properties, I mentioned that the pKa and the hydrophobicity are very important properties. Why? Because the pKa is going to determine whether you have a protonated or a deprotonated or a zwitterionic form of your amino acid. And if you remember, I mentioned that the histidine amino acid residue has a pKa of 6, okay, and it lines a lot of active sites of enzymes, the sole reason being that the pKa of histidine, this pKa value we are talking about, this pKa of histidine is close to the physiological pH of 7.4. Okay. So, it can act, we will see how it does that later on in a later class. It acts not only as a base, it can also act as an acid. Okay. Another important property that we learnt about amino acids was the hydrophobicity. So, that is also going to be important in the active site residue lining. The flexibility, because we have to have residues move over to make way for the substrate to come in, and definitely the reactivity. So, now if we go back to see what other properties we have, oh my God, let's see, how do we get back here? Okay. So, look at the enzyme active sites that we have here. Okay. These are three typical enzymes: chymotrypsin, trypsin and elastase. Now, these are what we have in the active sites of these proteins. Okay. We will see what these proteins or what these enzymes do as we proceed in the course. But for now, what we have here is we have two glycines and a serine. Here we have two glycines and an aspartic acid. Okay. The aspartic acid we know is a acidic amino acid residue. It has a negative charge associated with it. So, it is likely that the substrate that it is going to bind to is going to be of the opposite charge, a positive one here. So, we see, what do we see here? We see a lysine here. Okay. So, if this is our enzyme active site, it is such that it will accommodate a residue that is counter in charge to the active site residue, and it fits in the active site. Okay. So, we have to have basically a fit of the specific substrate that we are talking about in the enzyme active site. Again, this is another protein called elastase, another enzyme rather that we can call now called is elastase, that has again two different groups in its active site, and it again acts on a different type of amino acid. So, each of these active sites have their own properties in deciding which substrate it is going to act upon. Now, if we look at enzyme classification, okay, we have simple enzymes and we have complex enzymes. What do we mean by them? For a simple enzyme, we have an enzyme that is composed of a whole protein. An example of a simple enzyme would be ribonuclease. Okay? Ribonuclease is composed of a whole protein. It is a simple enzyme. If you have a complex enzyme, it is not the protein alone that can act on the substrate, but it will be composed of a protein plus a relatively small organic molecule. A complex enzyme is what is called a holoenzyme. It is comprised of an apoenzyme, which is the protein part, and a prosthetic group or a coenzyme. So, for the complex enzymes, we have a holoenzyme, that is the whole enzyme basically, the holoenzyme that is comprised of an apoenzyme and a prosthetic group or a coenzyme. What is a prosthetic group? A prosthetic group is a small organic molecule that is bound to the apoenzyme, which is a protein, by covalent bonds. That is what a prosthetic group is. So, if you have a holoenzyme that contains a prosthetic group, then it is attached to the protein that is the apoenzyme by covalent bonds. In contrast, when the binding between the apoenzyme and the non-protein component is non-covalent in nature, it is then called a coenzyme. Okay, so that is the difference. So, we have in this simple very ordinary classification, we would have two types. One is the simple enzymes that comprise just of whole proteins, for example ribonuclease. Complex enzymes that have a, what do they have? They have a protein part, and along with the protein part they have a small organic molecule, moiety, either attached to it covalently or just associated with it. Okay. If it is attached covalently, it is called a prosthetic group. If it is just a non-covalent association, it is called a coenzyme. There are other classifications of enzymes which you will have to know about, which we will be doing in the next slide. They are on the type of reaction that they work upon. You have to recognize that these enzymes are biological catalysts. They are proteins themselves and they act on specific substrates. Now, based on what substrate or what reaction they are going to catalyze, we have classifications and we have 6 different groups of enzymes. These are these groups. I will go into detail about this. The first one, now all these enzymes are called, if you look at the names at the end, they are suffixed by ase. Okay. So, an oxidoreductase from the name itself suggests that it would be a redox type of reaction that it would catalyze. Okay. So, an oxidoreductase would act on the chemical groupings either to add or remove hydrogen atoms. So, from the name itself you can actually figure out the function of the specific enzyme. So, what is the oxidoreductase doing? It is involved in a redox reaction. It acts on groups to add or remove hydrogen atoms. A transferase, what is that going to do? It is going to transfer. What transfer what? Since you are looking at specific reactions, it is going to transfer a functional group between the donor and the acceptor. Okay. So, that would be a transferase. We have a special name for groups that transfer phosphate. They are called kinases. Okay. Later on when we will be doing bioenergetics, you will see how kinases are extremely important in the transfer of phosphate from ATP to other molecules, because this ATP is our currency of energy. Okay, this is something that probably you have studied in your 12th standard, where you know that ATP is our energy currency. Okay, it provides all the energy. So, there is a specific name for the transfer of this high energy phosphate, and the phosphate transfers are done by kinases. Okay. So, a transferase would transfer a functional group between a donor and acceptor molecule, and the kinases are the special groups of transferases that transfer phosphate groups. Hydrolases, what does the name mean? Hydrolysis. Okay. So, we have hydrolases that would do what? They add water across a bond. In the event of doing that, what happens? It hydrolyzes the bond. We have lyases. What do lyases do? They add water, ammonia or carbon dioxide across double bonds, or they remove these elements to produce double bonds. So, what do? The lyases, they are the ones that are going to add these small molecular moieties across double bonds or remove them to form double bonds. Isomerases. What does the name sound like? An isomer. So, what is it going to do? It is going to bring about an isomerization. An isomerization reaction is going to be catalyzed by an isomerase. So, it will carry out or catalyze the isomerization, say from an L to a D form. So, basically what is it doing? It is shifting the chemical groups. If you have an asymmetric carbon atom, you know you can have an L form or a D form. What is the difference? The difference is in the position of the groups. So, this isomerase can change the position of the groups about the asymmetric carbon atom, giving rise to either an L isomer or a D isomer. So, we have the name isomerases. Ligases. What does ligation mean? Linking together, right? So, a ligase would catalyze reactions in which two chemical groups are joined or ligated with the use of energy from ATP. So, a ligase would catalyze a reaction where there would be chemical groups that are joined together. Okay? So, these are the 6 different classes of enzymes that are used, we will see later on, in what is called universal enzyme classification. Each enzyme has its own identity that sort of looks like an IP address. Like a computer has an IP address, your enzyme has an enzyme classification which looks exactly like an IP address, like a 3.3.102.11.3. That is an enzyme classification that would belong. So, what the first number actually is which group it belongs to here. Okay? So, if it were 1 dot something, it would be an oxidoreductase. Okay? So, that amounts to the enzyme classification. So, what are the 6 types we have? We have an oxidoreductase, a transferase, a hydrolase, a lyase, an isomerase and a ligase. Okay? And what you need to know is which reactions are catalyzed by which enzymes, and all you need to actually follow is what the name means. If you understand what a ligase means, you know that the chemical groups are joined by this enzyme. If you know what an oxidoreductase means, what does it mean? It is involved in a redox reaction. Okay? Okay. Now we come to this thing that I was talking about the delta G and the delta G dagger there. What do we have here? We have now not an A plus B or a P plus Q anymore. We now have an enzyme and a substrate. Okay? What is the enzyme doing? The enzyme and the substrate actually form what is called an enzyme substrate complex. Okay? We will go into the details of exactly how this is formed or what is actually going on here, but we have an activated enzyme substrate complex here that is eventually going to lead us to our product. Okay? So, we have a delta G associated with that. What is this delta G? This is the free energy change for the system. It is a thermodynamic quantity. It is the free energy change for the system. But the delta G dagger that we have here, what is that? That is the free energy of activation in a reaction. It is related to the rate or the kinetics of the system. And thermodynamics, you know, does not provide any information about the rate of the system. It is just going to give you the delta G thermodynamic quantity that is going to tell you whether the reaction is spontaneous or not. Okay? So, if we just consider 2 reactions here, say we have a delta G for an uncatalyzed reaction. An uncatalyzed reaction that corresponds to 107 kilojoules. Okay? And then we have, so this is just delta G corresponding to the, so this is what, if I put this, what does this mean? It means it is the activation. when I say this is there for the catalyzed reaction, is this going to be larger or smaller than that? Smaller. Why? Because my reaction is now catalyzed, my energy for the activation has decreased. So, if I want to find out how the rates have changed, which reaction or which equation do I use? Which expression do I use? I use Arrhenius expression. What is Arrhenius expression? A e to the power, okay, this is our EA now, by RT. So, what can I do? I can find a K value. Now, this is small k. Small k is for rate always. Capital K is for equilibrium. It is never the other way around, and you should never make that mistake. K, capital K is for equilibrium always, and small k is always for the rate. So, we have a small k for the uncatalyzed reaction. I have a small k for the catalyzed reaction. How do I determine it? All I have to do is plug in the values here. A, if we consider the pre-exponential factor to be the same. So, how I have to be careful about units here, kilojoules, 8.314, and by default we usually use 298. Fine. What about my catalyzed? A E minus 46,000, 8.314. Remember to use the right R also, 298. So, I can find out how the rate has increased for the catalyzed reaction as compared to the uncatalyzed reaction. It turns out that this is approximately 5 into 10 to the 10. So, what am I saying? I am saying that when I reduce this energy of activation, I have reduced this energy of activation, and what have I done? I have increased the rate 10 to the 10-fold basically, right. So, I have a uncatalyzed reaction, a catalyzed reaction, and then I have associated with it the change in the rate due to the reaction being catalyzed. Whether it belongs, whether the catalyst happens to be an enzyme or any other catalyst, it is the same thing. So, what do we have here? We have our enzyme plus substrate, and we have our enzyme plus product. Okay. So, what is our catalyst? Our catalyst is the enzyme. If you notice, what do we have in the beginning? In the first slide that I showed you, what was the first slide? We had A plus B going to P plus Q. What do I have here? I have E plus S going to E plus P. So, what is my E? My E is my catalyst that is transforming the substrate to the product, but itself is remaining unchanged. Okay. So, it is not like a normal reaction where you would have A plus B going to P plus Q, it is E plus S going to E plus P. E remains as it is in this reaction. Okay. So, what do enzymes do? Enzymes accelerate reactions by lowering the free energy of activation. How do they do this? They do this by binding the transition state of the reaction better than the substrate. Enzymes exhibit saturation kinetics. We will see what this means in a moment. Now, how do I determine the catalytic activity of an enzyme? There must be a measure that tells me whether this enzyme is good or bad. Okay. So, what is the measure of that activity? The measure of the activity of an enzyme is called its turnover number. Okay? The turnover number is defined. So, how would you define a catalytic efficiency? An efficient enzyme would be one that could transform more of the substrate to the product, right? That would be an efficiency of an enzyme. So, the turnover number is defined as the maximum number of moles of substrate that can be converted to product per mole of catalytic site per second. What do we mean by a catalytic site? Remember, I showed you some diagrams where we had an enzyme active site. Okay. So, what are we doing? In that enzyme active site, there are substrates that bind to the enzyme active catalytic site or the active site, and they convert the substrate into product. As they do that, the enzyme retains its structure and activity so that it can convert another substrate to product. But there is a turnover number that is going to tell us the catalytic efficiency, and that efficiency is measured by how many number of moles we can transfer of the substrate to the product, the conversion per mole of catalytic site per second, because you have to remember it is a rate that we are considering, right. So, you are looking at the maximum number of moles of substrate that can be converted to product per mole of catalytic site per second. Okay. Now, what happens to a protein when we heat it? It denatures. An enzyme is a protein. So, what do you have for normal reactions when you increase the temperature? The rate increases, right? For enzymes, what would you expect? You would expect that there would be an optimum temperature at which the enzyme is going to act, because beyond that it is going to get destroyed. If it gets destroyed, then the enzyme active site is destroyed. As a result of that, what is going to happen? The substrate cannot bind, and obviously the product cannot form. So, we have an optimum temperature that, if we do a percent activity versus temperature curve like this, then we are going to have an optimum temperature for the highest activity of the enzyme, and you realize that at low temperatures the enzyme is not going to function. At high temperatures also the enzyme is not going to function, because it has to have an optimum activity, especially of course the activity is also going to, if it considering the reactions that take place in our body, then it is going to be an optimum of 37 degrees centigrade, right. How about pH? If we add too much acid to the protein, it is going to depend on what? It is going to depend upon the amino acid composition of the protein. You have to remember the enzyme is a protein. So, the amino acid composition of the active site is extremely important in determining which pH it is going to act at. Okay? So, if you look at the slide here, there are certain graphs here corresponding to the relative activity versus the pH. Okay? This first one here is pepsin. If you remember, you studied in school about enzymes, if you had biology, where pepsin acts in our stomach where the acid is at low pH. So, the pH of the acid in your stomach is 2. Pepsin acts at pH 2. What does that mean? It means that there are certain groups in pepsin that are active at a pH of 2, right. If we go to any other enzyme, there are very few enzymes that act at very low pH or very high pH. The normal activity that you would see is what you see for trypsin here, where you would find an optimum around 7. 7, 7.4, 7.5. Okay, that would be the pH optimum for a usual enzyme. Pepsin acts in the stomach where there is a high level of acidity. Okay, so the effect of pH on its optimum activity is at a pH of 2. In this case, for example, trypsin, the optimum pH activity is around a pH of 7. Okay, that is the normal case that we would observe. Okay, now we get to the kinetics. What is happening here? We have an enzyme plus a substrate that is going to form the enzyme substrate complex. Now, in this enzyme substrate complex, we have a pre-equilibrium step. This step is our pre-equilibrium step. This is a very simplistic way of writing an enzyme kinetic reaction, but nevertheless we will consider the kinetics of this reaction now for the definition of certain terminologies. Now, the first reaction that we have here is a pre-equilibrium, which means it has a forward rate constant and a backward rate constant, right. If we consider the forward rate constant to be small k1 and the reverse rate constant to be small k minus 1 and this to be k2, then we have our enzyme plus substrate. So, we basically, if we just draw what it looks like, we have say an enzyme and we have our substrate. They are forming an enzyme substrate complex. Okay? Then whatever reaction is to occur at the active site occurs, then what do we get? We get back the enzyme, but say our product looks like this, right? Because our substrate has changed now to the product, but our enzyme remains the same. That is what is unique about these catalysts. You have to understand that these are all chemical reactions that are going on in the active site, but it reverts back to where it has to be after the reaction in the event forming the product. Okay? So, now we are going to see how we can get to expressions for enzyme kinetics. So, if I just get in here. Okay. So, what do we have? You do this along with me. We have E plus S going to in a K1 and a K minus 1 going to an ES complex forming E plus P. Okay. Now, I am going to define a velocity for the reaction. A velocity for the reaction. What is this velocity? It is going to be V. It is going to be, this is going to be K2. The velocity of the reaction is going to be the rate at which the products are formed. Okay? So, it is going to be equal to K2 ES. What is the rate at which products are formed? It is dP dt, right. dP dt is the rate at which products are formed. So, I have my dP dt, which is actually nothing but the velocity. Now, what do I want? I want an expression for ES. To get an expression for ES, I have to consider d ES dt, right. So, if I have now a steady state, you have studied steady state kinetics, what is that? That is telling you that the rate of its destruction is equal to the rate of its formation, right? So, the production and its destruction is at the same rate. So, if I apply that to the expression that I have here, what can I write for ds dt? I can write K1 enzyme concentration, substrate concentration, minus, why minus? Because it is being destroyed in the backward reaction, and minus K2 ES, right? So, what do I have? I have an expression that tells me that this ds dt is going to be K1 ES because it is formed by K1, it is destroyed by K minus 1 and K2. Now, if I am to apply the steady state here, what do I equate this to? I equate this to 0. Why? Because its rate of formation is equal to the rate of destruction. So, there is no change of the concentration of the enzyme substrate complex with time. If there is no change with time, then this is what? This quantity becomes 0 because I am at a steady state, right? Okay. So, now if I am at this steady state, now what I will get is I will therefore get a new expression for ES. Okay. Now, what expression do I get for ES? It is going to be, what did I have? I have, let us just write this once more. I have dES dt was K1 ES minus K minus 1 ES minus K2 ES. What did I do? I equated this to 0. So, I can get a value for ES. What is that? That is going to be K1 ES divided by K minus 1 plus K2. Fine? Okay. Now, what do I know? We have to remember that when you are doing this reaction, there are certain quantities that you have measured. It is your experiment. What do you know? You know the amount of substrate you have added. You know the amount of total enzyme that you have added. But you do not know at what time how much enzyme substrate is actually being formed, right? So, what you know is these are the quantities you know. You know what S is, and you also know what the total enzyme concentration is, right? Now, at any time t, the total enzyme concentration is going to be what? Whatever free enzyme is left plus whatever has formed the enzyme substrate complex, because the enzyme cannot go anywhere else. It either is free or it has formed an enzyme substrate complex, right? So, that is what our ET amounts to. Okay. So, now if I change the expression and instead of the enzyme concentration, I write ET minus ES. I can write this for the free enzyme. Where do I have this quantity in my expression? Here. So this is where we are going to now substitute this. So do that. So if we do that, what do we get? We get k minus 1 plus k2 Es is equal to k1 Et then minus Es that is what I have, right? So what can I now do? I have another expression for Es here which I can take over onto the left hand side, right? So if I do that, I will amount on the right hand side to k1 ETS. If I take this Es part over onto the left hand side, what will I land up with on the right hand side? A k1 ETS. And what will I have on the left hand side? Let's just do it. I will have on the left hand side a k minus 1 plus a k2 plus a k1 S all multiplied by Es, and what is this going to be equal to? K1 ETS. Now we are going to use some more information here. The velocity of the reaction. What was the velocity of the reaction? It was K2 ES. I am going to use another term here now. If this is K2 ES, I can define a Vmax. The Vmax is the maximum velocity the enzyme can attain. And what is that a measure of? That is a measure of the total enzyme concentration. Because if all the enzyme were to react, then it would attain the maximum velocity possible. Okay, now this is something you should get very clear. If you are considering the maximal velocity, it is the highest reaction rate that can be attained because all of your enzyme is going to be saturated with the substrate. So it is going to be K2 ET. Okay, so basically if we work out this whole reaction by substituting V as K2 ES and putting Vmax as K2 ET, if we multiply both sides by K2, because instead of, I am not working it out completely, but it is just algebra. Instead of K2 ES here, we are going to put V. So I am going to have on the left hand side a K minus 1 plus a K2 ES, not a K2, a K1S, sorry, a K1S plus a V actually, because we are looking at this and this together with ES, and the K2 and the ES form the V. And what do we have on the right hand side? We still have K1 ETS. Now if I multiply both sides by K2, I can put a Vmax form here. Okay? Eventually what we are going to get is, we are going to define another quantity that is going to be a combination of the rate constants. It is the Michaelis constant that is equal to, you can write this down, K minus 1 plus K2 divided by K1. This is another quantity that we are going to use, and the final expression after you do all the algebra is going to work out to V equal to Vmax S divided by Km plus S. Okay? That is your final expression that you are going to get after you do all the algebra. Now, if I want to have a physical interpretation of what Km actually is, the Km value, if I want to have a physical interpretation of what it actually means, then what you can get is, what is the expression? The expression is V equal to Vmax S divided by Km plus S. Now if I make this velocity Vmax by 2, okay, if I just say that the velocity is half attained, the Vmax is half attained, then I have Vmax by 2 equal to Vmax S by Km plus S. Okay? And if you work out the algebra, you will get, in this specific case, Km equal to S. So what does this mean? It means that the Km, or the Michaelis constant, is the substrate concentration when half the maximum velocity is attained. Okay? So all you have to do is just do the algebra. Now let's go back. So if we look at our enzyme kinetics, we work through the whole set of expressions. Now what do we have from the expressions? We get the Michaelis-Menten kinetics, and this is the expression that we got there, that V is equal to Vmax S divided by Km plus S. What are the features of enzyme kinetics or Michaelis-Menten kinetics, as is it called? It assumes the formation of an enzyme substrate complex. There is a pre-equilibrium where the enzyme substrate complex is in equilibrium with the free enzyme. Then the breakdown of the enzyme is slower than the formation of ES and the breakdown of ES to reform E and S. Okay? So basically what we're looking at is, we're looking at a picture like this. That's exactly what happens. What we have is, we have the velocity and we have the substrate concentration. As you increase the substrate concentration, you are going to have saturation. Why? You are talking about an enzyme. It is a protein. It has a minimum number of active sites. You have a limited amount. Okay? So even though you increase the substrate concentration, the enzyme has a definite capacity to accept the substrate. So at a time, you are going to attain saturation, and at high substrate concentration it is going to be independent of the velocity is going to be independent of substrate concentration, where you have 0 order kinetics. Initially you have first order kinetics at low substrate concentrations, where V is proportional to S. Okay? And what is Km? This is Vmax, this is half of Vmax, this is Km. It is a substrate concentration at which half the velocity maximum is reached. Okay? So, what we did to do today was understand what enzyme kinetics is, what enzymes actually do, and their specific classifications based on the types of reactions that they catalyze. Next day we will consider more of this enzyme kinetics and how we can inhibit the kinetics of enzymes. Thank you.